Okay, there we go, 2-1. 2-1's all about functions. Functions are, you probably know a fair bit about functions already. We're going to get a little more theoretical about them. Functions are a relationship between inputs and outputs. That's what a function is. A toaster is a function, for example. Just to give you a real life practical example. A toaster sets up a relationship between bread, that's not how you spell bread, between bread. You put bread into the toaster, what comes out? Toast. You put frozen waffles into the toaster, what comes out? Toasted waffles. So a toaster is a function, meaning what? Meaning it's a connection. In fact, you could draw the arrows this way. You could just draw the arrow straight from bread to toaster and frozen waffles to toast waffles. And that relationship, that function, call it F, call it G, call it H, call it toaster, is the relationship between inputs, X values, and outputs, Y values. And this is called the domain. You heard that word before? All the X's, things you put in. This is called the range. All the things that come out, the Y values, the outputs. So that's all a function is in the end, is a connection, a relationship between inputs and outputs, X's and Y's, domain and range. Put stuff in, it does something to it and spits something out. That's all a function is a relationship like that. So they're giving us a function relationship right here. Looks like it's first name, last name. John Doe, Katie Smith, Kia Hill, Marcia Brady, and Jan Brady. Now, so what I really should say is all these are relationships, and certain kinds of relationships are called function relationships. Other ones are not. So a relation is a function when every X input goes to only one Y. That's the crucial rule. We want every X going to only one Y. If you think about it, that's how you'd want your toaster to work too, right? When you put one thing in, you don't want like different things coming out. You don't want to put in bread, and sometimes out comes toast, sometimes out comes waffles. Who knows what's coming out of that thing? That would be a broken toaster, right? That'd be kind of an amazing toaster. But anyway, that's not what we want. So relation is you want one X only leading to one Y. Okay, so here's the question. Is this relation, it's certainly a relation, but is it a function kind of relation? The answer is actually yes. Now you might think, wait a minute, what about this, Mr. You just said only one X to one Y. What about that right there? That's fitting that rule, right? Let's check it. Marcia, she's an X. These are the X values. These are the Y's. Right? Marcia's an X. Does she go to two different things? Does Marcia have two different last names? No. She's only got one last name. It's Brady. Well, how about Jan? How many Y's does he go to, or she? One. So it's okay to have two X's going to the same Y. What would not be okay is if John also had another last name, Doe or Jones. That would make it not a function kind of relation. Does that make sense? That would violate this rule. That would be an X going to two Y's instead of to only one Y. It's fine if two X's go to the same Y. We're not saying anything about that. This is okay. We just don't want one X going to two Y's. So this one's a yes. That's why I checked the yes there. And now it says list the domain. What's the domain? Well, the domain is this, huh? So I'll leave that to you. That must be John, Katie, Kia, Marcia, Jan. Yeah, it's this right here, huh? This is the domain. If they're going to ask you the range, what's the range? This is the range over here. So domain and range is just inputs and outputs. Make sense? So far? So we're going to look at that idea. This is the fundamental. This is the golden rule right here. A relation is a function when every X goes to only one Y. That's the golden rule. We're going to apply that in various situations. We're going to say, how does that look in graphs? How does that look when you list points in a set? But it's just going to be this golden rule over and over and over again applied to various situations. So remember, that is the fundamental rule. So how about that one? Is that one a function? Yeah, because this x is going to 2y, so it's no, not a function because of this problem right there. Right? Blue, oops, scribbling here. Blue goes to two things, two outputs. So that's a problem. You can't have 1x go into 2y. So that one's a no. On that one. So you know what I think will help on this one? You know how points go. It's x and y value, x and y, x and y, x and y. So why don't I just make an x column and a y column? I think it's easier to see if we do it that way. -2, -7, 8, -6. And we can even put them on a graph if that helps. -9. Well, we'll do that in a minute. Doesn't really help, but it shows us some other insight. Anyway, so there we go. There's the xy points. They're just listing a bunch of xy points in a set. I'm going to separate them because it's easier to see. So, you know, we're basically saying here's the relation, x goes to y. Is that relation a function? No. It's not, because -2, so it's not a function. It's no, not a function because -2 goes to two different outputs. So that wrecks it. Does that make sense on that? Pretty easy, right? It's not a function for that reason. Hey, if we looked at a graph of that, do you know what we would see? Let's put those dots on a graph. This is not required. I mean, we're done with the question, but you will see some other insight. Let me do the point. What's this point? This is -2, -7, right? So back 2, down 7, 1, 2, 3, 4, 5, 6, 7, right there. So back 2, down 7. And this point is back 2, down 3, right there. Those two dots. What do you see about those two dots, and what do you remember from algebra about functions?
Is that class the vertical line test?
Yeah, very good. Do you remember the vertical line test? If any vertical line on a graph, you know, there hits two dots, it's not a function. So that's called the vertical line test. Any vertical line must hit only one point, not two. So to be a function. To be a function. So do you see how that's just the same thing again? That's just the 1x leading to 2y's. It's just a way to see it visually, graphically, right? Because if a vertical line hits 2 points, that means it's the same x value leading to two different y's, huh? Same x, two different heights, right? That's what it means. You see, the vertical line test is just a restatement of the same basic fact on a graph. That's all it is. All right. Easy rule. Well, I hate rules without reasons, so I'll give you the reasons too. So basically, these will be super easy. Let me just give you the rule. The rule, so now they're going to give me like an equation, and they're going to ask me, hey, is that equation a function kind of equation or not? What's the rule for well, it's not well, it is an equation, for a rule for a function. Let me just write it that way. The rule for a function, if it has x to an even, no, that's not true, y. If it has y to an even power, or if it has absolute value y, or if it has plus or minus anywhere, if it has any of those, it's not a function. I'll show you why in a minute. Otherwise, it is a function. It's super simple. It's all you got to look for. Good thing to put on your 3x5 card for the next test, for the first test. So yeah, you just basically look for y to any even power, like 2, 4, 6, 8, any of those. So that'd be like, you know, y squared, y to the fourth, etc. Y to any even power or absolute value of y, or plus or minus anywhere in the equation. That means it's not a function. Otherwise, it's good. It's a function. So we just simply look at this thing and go, okay, do we have y to an even power? No, it's just y to the first, right? Do we have absolute value? Do we have plus or minus? No, no, no. So it's okay. It's a function. Just that quick. Now, I haven't given you good reasons for that, but I'll show you in a minute. Does that make sense? So these will be super quick for you in the homework. That one's good to go as long as it doesn't have an even power on y or absolute value or plus or minus. What maybe I should write here while you're copying out. Why is that? Why would those be the issue? Well, remember our original function rule. Keep that in your mind. 1x is only supposed to go to 1y. If you have an even power on y, like y squared is x or whatever, that would not be a function. Why? Can you see it now? See why that would be a problem? What if you had the x 9? What two different y values could lead to the x value of 9? 3 and negative 3. See how that one x of 9, would go with two different y's to make it true? Those would both be true of that equation, wouldn't they? We'd have to say the point, whoops, just jumped it funny there. We'd have to say the point, x is 9, x goes first, right? I got to put x first. At 9, whoops, right, funny. We'd have to say the point 9, 3 and 9 minus 3, right? xy would both be on the graph, and that's not allowed. That's the same x leading to two y's. You see, when you have y to an even power, it buries the sign, doesn't it? So you get two different y's that both work the same. You don't want that. You can see why the absolute value is going to do the same thing, right? Put absolute value on y, right? Plus or minus, right? If I had that, then this could be, if I had absolute value, then this could be plus 9 or minus 9. Again, that would be two y values going with the same x, wouldn't it? And then finally, the plus or minus thing, obviously. X is plus or minus 3y or whatever. There's just two options right there. So that's going to wreck it. So those are the things that will give you two y's going with the same x, and it's not a function. Otherwise, it's good. That's all you got to look for. So number 8, we got y equals 4 over x plus 3. They're asking, is it a function? Yeah, let's go yes. Right, yes. Because there's no y's to the second power, or any even power, there's no absolute values, there's no plus or minus. Done. Good? You're wanting a lot of those on the next test, right? Like half the test that way? So y is plus or minus square root of 2 minus x squared. Is it a function?
Yes.
No, plus or minus, right?
Plus or minus.
Not a function. Oops. Function. Not a function. Got plus or minus. That quick. It's got plus or minus. Y to an even power. Absolute value. It's out of there. Not a So x minus 1 is y squared. Is it a function?
No.
Nope. Y to an even power. Not a function. Done. Nothing more to do. Two y's lead to the same x. Right? You might wonder, what is that? Well, I could make x 10, for example, and y plus 3 or minus 3 squared. Right? 10 minus 1 is 9. It's plus 3 or minus 3 squared. Not allowed. Same x. One x value leading to two different y values. Not. How about this one? Y equals 4x squared plus 2x minus 4. Is it a function? Yes, function. You might wonder about that power, but it's not on y. Y's just to the first power is okay. We don't care about x squared. We're fine with x. X have any power he wants. We're just focused on y. Remember, it said y to an even power would be bad. We have y to the first power here, so that's fine. We're good. That one's a function. All right, so you remember this from your algebra days, right? 4x squared, I think that's one we just had, plus 3x plus 3. They want us, first off, f of negative 3. I've already got the answer there for you. Remember how to plug in the functions? Go ahead and plug that in. Just make sure you can get a 30. Just plug in the negative 3 there. Use your calculator. Remember all that? Just plug in negative 3, like that. And then that is, what's that, 4 times 9. Minus 9 plus 3. 30, yeah, it is 30. So there we go. Just plugging into functions. Remember how that works? Just plugging in everywhere you've got x. Is that good? Feel free to stop me. I know I'm flying over this stuff. It is review, but I'm glad to stop when there's some little rusty thing from the past that you want to talk about, feel free to jump in and let me know. Is that okay? Good there? All right. Now, how about part B over here? F of negative x. So you know what you do, right? You're just going to plug in here and here negative x in the parentheses, right? Whenever we plug in, put it in parentheses. So what's that? 4x squared minus 3x plus 3. This minus is canceled by the squaring, huh? Good with that? Remember all that? And now that's different. Let me come over here. That's okay, I'll erase this. That's going to be different than part C. This is part B over here. Part C, where they're putting the minus in the front. They're just wanting to make sure you understand the difference between part B, where the minus is plugged in to the function. It's in there with the x. And part C, where the minus is in the front. What does that do differently? That just means you put minus on the whole thing. So you just put the minus in the front of the whole thing. Right there. Like that. And then the minus distributes to all three. That's our answer. Is that okay? Well, that just means the minus is in the front of the whole thing, right? Minus is in the front of the function, the entire function, instead of plugged into the function. Why did I put these parentheses here? Where'd they come from? Well, that's how I said the whole thing, right? Because this means minus on the whole function. If I don't put if I leave these parentheses off, yeah, then the minus is just on the front part, which is not true to what they said. They said minus on the whole function. So the way I do the whole function is I put parentheses, right? Parentheses are really, I know we think of parentheses as multiplying, and they often do that, but they're really a grouping symbol. That's what they mainly are. They say, hey, this group hangs together. And that's what I need to say there, because the minus is on the whole function, so I can put the minus on the whole thing. And the way I say the whole thing is those parentheses, right? And then it distributes. You could skip the parentheses step and just go right to here. It's fine. As long as it gets to everybody, it's all good. Now, the hardest one is part D, right? So if you're ready, we'll go on to part D. It's real important for calculus. You'll do that exact thing in part D, so let's do that. So part D says, all right, take that function now. Let me come back up here. F of x, 4x squared plus 3x plus 3. And now it's saying, all right, now put in x plus h. So I got to plug in the whole x plus h. It's going to be, a bit of work. So x plus h, x plus h. Is that good to there? We good so far? Plug in x plus h. So now we got to FOIL things out. So this is x plus h, kind of messy here. Oops. And then remember, so here again is just like the one we did a few minutes ago. I'm going to do these parentheses first. Just leave the 4 sitting in the front. I'll do the parentheses first. So I'll get, going to distribute here. X squared plus xh, boom, boom, plus xh plus h squared, and then distribute this guy. 3x plus 3h plus 3. Okay, and then gather like terms. xh and xh is 2xh. Remember that? When you're adding, you just add the numbers in the front, right? It doesn't make x squared h squared. That's when you multiply, huh? I'm just adding 1 and 1 is 2xh, right? When you add, you just add the numbers in the front. You don't mess with powers. Powers is just when you multiply. And then distribute that 4x squared, 8xh plus 4h squared plus 3x plus 3h plus 3. Whew, we're almost there. One more step, hopefully. Or no, we're just done? Is there anything like terms there?
No.
All right, we're just done. Nothing more combines. So there we go. So you got to do a lot now in calculus. That exact thing, they have you plug x plus h into functions. Good on that? That okay? Good with all that algebra mess? All right, I'm going to move along if it's too. So part C. So we're going to take this function, f of x is 3x over x squared plus. I'm just going to do part C here. And what does part C say? Part C says, give me negative. Well, bring it down here. Give me. Part C says, give me negative f of x. So, so that means put negative on the entire function, right? Now, that can be a little tricky. What does that mean exactly? How do you put, right, they want me to put on part C, negative on the entire function. Do you notice what I did? You can see by the answer here. I just put it in the top only. That's one correct way to do it. So are you aware that when you have a negative on a fraction, you put it on the top only or the bottom only, but not both? Let me just do a normal fraction. Like what if I had a half? What if I had a negative in the front of a half? You could put the negative on the top only, or you can put the negative on the bottom only, but you don't put it on both, huh? Why would that be wrong? That'd be positive, huh? Two negatives, that'd be actually positive, so that can't be the same as a negative on a half, huh? So this issue will come up again several times, so make sure you're real clear on it. When a negative is on a fraction, it goes to either the top only or the bottom. It's your option, whatever's easier at the moment. I usually just go to the top, but not both, right? So I just threw it up here in the top. Now, I could have put it on the bottom. If you do put it on the bottom, it's got to hit the whole bottom. So it'd have to hit both those guys like that. That's a fine answer to do. MathExcel knows that it'll take either one. Both are right. Is that good? On that, so that's part C. Part D would be the same thing. Just plug in the x plus h. I'm going to move along. You're okay? So domain. Domain, as you know, is the possible, or I should say allowable, same thing, x values. The allowable x values. That's what domain is, right? So let's talk about it. Let's go back to, let's make this as real as we can, and then I think then the abstract stuff will make more sense. If I was to say, hey, what's the domain of my toaster? That sounds pretty weird. But what do we mean? We mean allowable x values. What are x? Inputs, right? Remember, a function is just inputs, outputs. X is y's. What are you allowed to put into a toaster? Well, you know, anything you want. Bread and frozen waffles and whatever. But you shouldn't put knives into the toaster, for example. That would be a bad plan. So we would say knives, silverware, are not in the domain of a toaster. Not allowed to plug that in, right? Microwave oven, that's a function. There's certain things you can put in there. There's certain things you shouldn't put in, plastics that are going to melt, and tinfoil is a bad idea, right? Not in the domain of a microwave, not to be put into, not to be plugged into. So that's what we're talking about. When we talk about the domain of a function, we're saying what can you plug in, what's okay and what's not okay. Well, basically, here's the deal. Here's the stuff that's not okay. Basically, everything's okay except a couple things that are not okay. What's not okay? Well, do you know, one of the things that's not okay is if there's a, number one, if you have a denominator, you set it not equal to 0 and solve. Because we never want denominators being 0. That's not okay. You aware of that? Is that comfortable for you? You know, like 3 over 0. You guys have your calculator? What does the calculator say if you go 3 divided by 0?
That'll be a sign accelerator.
Yeah, it'll just say error. It's technically undefined. Calculator will usually say error or something like that. Syntax error. I don't know what it is. Different calculators say different things. But you can't have 0 underneath a fraction. Why not?
Because it'll be undefined.
Yeah, but why is it undefined? Why don't we just say it's 0?
Fraction basically their division 3 times 0 is not possible.
What's that? 3 times 0 is not possible?
No, 3 divided by 0.
Yeah, why is it not possible?
Because it'd just be 0.
Yeah, why isn't it just 0? Goes in there 0 times. Right, what's 0 in the top?
0.
That one's just 0. Why isn't the other one just 0?
Because you can't put 3 into 0.
Yeah, you can put, yeah, this is putting 3, this one's putting 3 into 0. Remember the bottom goes into the top?
Right. No.
It's getting a little confusing. Is math, let's stop for a second. Let me, 1 minute of, minute and a half maybe. Is math real? Is math real? This goes to philosophical underpinnings for just a second. Is math real? I mean, math itself. I mean, I know we do all kinds of real things with math, but I'm being a careful philosopher here for just a second. Is math itself, narrowly defined, just math, not the applications of math, but just math all by its own self, is that real? Well, no. Right? What if I said, hey, I was on the way to class today and I saw 3. There it was. I saw 3. I saw math. You know, you'd think, what do you mean, Mr. Aaron? You saw 3 cars or 3 people or, 3 solar, you looked at the solar eclipse too long yesterday, didn't you, Mr. Aaron? What are you talking about? You saw 3. No, I didn't see 3 people or 3 cars, 3 objects of any kind. I just saw 3. You go, what do you mean you just saw 3? You saw like the number 3? Like written, spray painted on the wall somewhere? Or what do you mean? I know I didn't see the number 3 written anywhere. I didn't see 3 objects of any kind. Those are all applications of math, right? I just saw 3. Well, I'm ready for the padded room, right? So math itself is not real. You can't taste it, touch it, or smell it, right? But it's just made up, right? We just made it up. Math is made up. I'm not even supposed to say that. Don't let the dean's right across the hall. Don't let her know. Class is over. I mean, what are we even doing here, right? Math is just made up. It is. It is. It absolutely is. Math is made up to describe things that are real. Math itself is not real. Well, that's what we have going on here. Math itself is not real, right? But we use it to do things that are real all the time. Real simple application. Obvious application. Noises. Right? Noises. Well, what do we measure the level of sound in? Decibels, right? Where'd that come from? When I make a sound, does it say I'm such and such decibels? No, it doesn't know. I'm just making a sound. We made up the whole decibel system, didn't we? And we put numbers to sounds. Louder sounds, we made this whole number. It has to do with the energy level, and we won't get into all the physics. But basically, physics came along, used math as a tool to take sounds and put numbers. Well, why? Why are we putting numbers to sounds? We're doing that. They don't have their own numbers. They just have higher power, higher energy. It's energy per square. What I'm doing physics again. It's energy density. Anyway, they just have an energy density bigger or smaller, and we're putting numbers on it. Well, because that's useful for life, right? Say you're having a hearing problem, and you go to the doctor, and the doctor says, hey, you're working at that factory? Tell your manager you can't be around sounds any louder. It's hurting your eardrum. You're going to wreck your hearing. Tell your manager at that factory you can't be around sounds any louder than... What's the doctor supposed to do? Any louder than this. Sorry, I'm spitting on the front row. What's he supposed? And you're supposed to. Okay, any louder than what was that, Doc? Louder than this. Little. I got it. Okay, and then you say it all weekend long. Then on Monday you go to your manager. Doctor said I couldn't be louder than this. That just wouldn't work, right? So instead we made up this number system, 100 decibels. He writes it on a prescription. You go to the office. You go to the factory and 100 decibels, and they have the equipment labeled with the decibels. It's helpful for life, right? Math is a made-up number system to help us live life, right? All right, so math is made up. So here we see this. This is not in the real world. That's why we say it's undefined, right? Think about real life. You know what fractions mean. If I said, hey, last night I was so hungry, I ate 1/3 of the pie. You know what that means. There was one whole pie cut into 3 pieces, and I ate one of them. Right? So, and what if I said, last night I ate 0/3 of the pie? Well, that's a weird way to say you ate no pie. But it's still true. You can, in the real world we live in, eat 0/3 of a pie. It's just a weird way to say you ate no pie. Right? But you can't do this. in the real world. That's impossible. Why? What the bottom number is cut into, right? How do you cut something into 0 pieces?
You don't.
Now you might think, oh, you just don't cut it. No. If you don't cut it, it's 1 piece, right? How do you cut something into 0 pieces? That is impossible in the universe we live in, right? Math can do numbers that way, but that doesn't fit reality. See, this is where we see math is not real. Math is just plug in numbers. It doesn't know what the real world we live in is. So we have to be wise enough to say to math, that doesn't happen in our world. So we never want 0 underneath a fraction. It's undefined. So that was a long story to tell you. 0. So therefore, all the time in math, we're always going to be saying, don't let denominators be 0. Because that doesn't exist in our world. There's no definition for that in our world. No application of that. Number 2, the other thing, is if you have a square root. So remember, we're saying what are the trouble spots? Like no knives in the toaster, right? We're saying no denominator 0. And then secondly, inside of a root, if you have a square root, what does that mean? What can you not have in a root that would not be real? Negatives. Those are imaginary. Remember that? So the inside has to be greater than or equal to 0, and then you solve. Those are the 2 things we look for. You tracking with me? You guys all know you can't have negative inside a square root, right? Like square root of negative 9 is imaginary. Right? Because there's no number times itself that's negative 9. Right? So it's imaginary. So all we do is we look for those 2 things. Otherwise, and let me just write somewhere, otherwise the domain is negative infinity to positive infinity, meaning all real numbers are possible. Anything's allowable. So let's look at this function right here. I've got a little room over here. So let me look at this function right here. What's our function? It is negative 7x plus 7. So does that have any domains? Any denominators?
No.
No, it's got no denominator problems. Does it have any square roots? No. So it's otherwise everything. You can plug anything you want into that function. Any number is fine. He's got no problem areas. Domain is all reals. Negative infinity to positive infinity. Is that good? So we've got x squared over 9x squared plus 7. So we right away go, oh, that denominator could be, I don't care about the numerator at all. Ignore it completely. We just say, hey, denominator, we got to make sure you're not 0. Right? If that denominator becomes 0, again, that's not real. So we got to make sure denominator does not become 0. So then so it's a not equals. You solve a not equals equation just like you would an equals. It's a not equals equation. Let's solve it. Jump the 7 over there. Becomes a negative 7. Oh, by the way, you might think, Mr. You just said when you got x squared, get a 0 factor. I'm changing the plan. If you have x squared and no x to the first, see how this one doesn't have x to the first? See, that whole process we did, yeah, I'm probably confusing. Let me try to be real clear. If you have x squared and x to the first, yeah, that's the whole get a 0 factor or the quad, negative b plus or minus square root of b squared minus 4ac all over 2a. Yeah, that's that whole thing. But if you just have x squared and no x to the first, that's easier. Get x squared alone and put plus or minus root on it. Do you remember that? So this is an actually easier kind. See how there's no x to the first power here? So I don't have to do all that factoring, quadratic. If you just have x squared and numbers, no x to the first anywhere, it's easier. Just get x squared alone and root it. So let's do that. So I'm going to divide both sides now by the 9. Let me get rid of this out of here. Divide both sides by the 9. And we get x squared not equal to negative 7/9. What's the next step? Yeah, you're going to square root. Let me bring it down here. Whoops, that's not plus or minus. What am I doing? That's not equals. It just looked funny. Not equals. That's a not equals. Not equals, not equals, negative 7/9. And now I put the root plus or minus. So rooting cancels squaring. X cannot equal X is not allowed to be. X is not allowed to equal. Plus or minus. You got to put plus or minus when you root. What's the square root of negative 7/9? It's imaginary. Remember, negative inside a root? So what? Okay, so what does that mean about our answer? X, you cannot be imaginary. Okay, I won't be imaginary. I'll be real. So X can be any real number. So in the end, the answer to this one is negative infinity to positive infinity. All reals are possible. You okay with that conclusion? Did you see that? If this had been positive 7/9, then I would have said, okay, inside the root. I don't care about the plus or minus outside. But you can't have negative inside a root. You can try it in your calculator. It's an error. You can't have the square root of a negative number. That's imaginary. There's no way a number times itself can be negative. So if you get negative inside root at any point, it's imaginary. So we're saying X, you cannot equal. You're not allowed to be an imaginary number. If that had been plus 7/9, I would have said, okay, X, you're not allowed to be plus or minus the square root of 7/9. That would have been a real restriction. I would have said, X, you can be anything, but you can't be plus or minus the root of 7/9. I would have left that as the answer. But because it came out imaginary, what I'm really saying is, X, you cannot be imaginary, which means it can be anything real. So it's really just this. Does that make sense? Mm-hmm. There's no way to make that 0. There's no way. There's no problem, really. Plug in anything you want. Anything you want, even 0. Squared times 9, since you square it, it's going to be positive, or 0. It's not going to be negative, right? Plug in a negative number, squared, it's going to be positive. Plug in a positive number, squared, it's going to be positive. Plug in 0, okay, it's 0. Times 9 is going to be 0 at the least, or something positive. Add 7, it's going to be 7 at the least. The lowest you can make that denominator is 7 by plugging in 0 for X. You're not going to make it lower than 7, right? So you're never going to make the denominator 0, you see. There's no way to make the denominator 0. There's no problem areas. All numbers are fine. That's another way to see it. If you can just see that, then don't even do the work. If you can just see it like, hey, that's not a problem, then just write this answer, go to the next problem. That's what it's got to be. Let's see. So 5x over x squared. Must I try that one? Find the domain, find the trouble spots, find what's not allowed to be plugged into that one. So grab only the denominator. Say denominator, you can't be 0. You could factor it, or you could just move the 9 over and plus or minus root it. Same two answers either way. Can you just see the answers right now? What squared minus 9 is 0? Plus or minus 3. You can just see it, write it down. Plus or minus 3, right? I'll do it more formally. I'll jump the 9 over. Right? X squared cannot equal 9. Put the roof on the house, put the root, and don't forget plus or minus. You got to have plus or minus when you do root on both sides. Because it's true, right? And so X cannot be plus or minus 3. Either plus 3 or minus 3. Say if you factored with the two parentheses, same two answers, right? Plus 3, minus 3. So X can be anything but plus 3 minus. Now, how do you answer that in interval notation? Yeah, let me help with that. If you go to the interval, the number line, and you say, all right, got a hole right here at 3, got a hole right there at negative 3. Anything else is fine. All the other numbers are fine, not plus 3. Not minus 3. But anything else, 2, negative 17, 2.9, 3.01, everything else is fine. But not 3 and not negative 3. They'll cause the denominator to choke, won't they? You put in 3 or minus 3, squared is 9 minus 9. The denominator goes 0. Not real. Imaginary. Not allowed. So you say all these numbers are fine, all these numbers are fine, and all these numbers are fine. How do you say that? Well, this is from negative infinity to negative 3. United with negative 3 to positive 3. United with 3 to infinity. That. See, parentheses, no brackets, because if I put a bracket on anything, that would include the number, wouldn't it?
Yep.
Remember, the straight edge to the bracket means you're straight on that number. but we're not straight on those numbers. We're just close to those numbers. So negative 3 is never included, nor is positive 3 by the parentheses. Question?
Could you also input it, or into the answer thing as like x cannot equal 3 and x cannot?
They said interval notation.
Oh.
So sometimes if they say that, but this one says interval. Good on that?
Well, wait, okay.
Let's try f of x is the square root of 4x minus 36. So what do you do? So remember square roots? I wrote things up a minute ago. Square root, you take the inside, and you say inside. You can't be negative, right? We can't, square root of a negative number is not allowed. That's imaginary. It's not real. It's not in the real world. So what we say, inside, you can't be negative. How do you say can't be negative? Greater than or equal to 0. That means not negative. You can be 0, you can be equal to 0, or you can be greater than 0, but you cannot be negative. So we say, all right, inside, so no, not the root anymore, just the inside, you must be greater than or equal to 0. Not negative. Then you solve it. Jump the 36 over, divide by 4. X, you got to be bigger than or equal to 9. Interval notation, it's a bracket 9 to infinity, right? Right on the 9, up to infinity. Any number 9 or bigger can be plugged into that function. Anything below 9 is going to choke it. Don't plug in. If you put in 8 here, that'd be 32 minus 36. That'd be negative 4. Square root of negative 4 is imaginary. It's not real. So we're not allowed to do that. Anything 9 or bigger is fine. Good? So domain here, square root of 6 over x plus 7. We say, all right, denominator. Notice this is both a denominator and it's inside of a root. It's both, isn't it? That x plus 7 is both a denominator and it's in a root. I don't care about the top. Doesn't matter to me at all. Just the denominator. So I say denominator. What do I normally say because it's in a root? Normally because it's in a root, I say greater than or equal to 0. But because it's a denominator, what does denominator mean? Not equal to, so get rid of that equals. Strictly greater than 0. Does that make sense? Because it's both conditions. The denominator condition says you cannot be equal. Denominator may not be equal to 0. That chokes it. So that's why I get rid of the equals part of the greater than or equals. Makes sense? So we end up just having x plus 7 greater than 0. Jump it over. X is greater than negative 7. How do you do that? Parenthesis is a parenthesis. Negative 7 to infinity. To that notation. They switch back and forth. Good on that? So watch out, that one's denominator and in a root. That is just strictly greater. Can't be equal. Let's try this one. All right, so they're giving me f is 8 plus 4 over x, and g is 4 over x. Okay. And they want me to figure out f minus g of 1. The part A is kind of off the screen a little bit now. F minus g of 1. What does that mean? That means you take function f and subtract function g. And so those cancel. That's just 8. And you're done. That was the answer to part A. It's just 8. That okay so far? I just subtracted f minus g. Got 8. Didn't even have to plug in the 1. If there was an x left, I would have plugged in the 1, but the x went away. Part B. They're saying find the domain. Now here's the trick. Here's the trick I wanted to show you. For domain, you must use f minus g before simplifying. So you must use f minus g before simplifying. What am I talking about? Well, look, when we subtract f minus g, it's right here. What happens? Well, these guys go away, and it's just 8. So technically, f minus g is just 8. And 8's got no problems. It's just 8. It doesn't have denominators, doesn't have square roots. I just say it's everything. But no. You gotta go right here, because that's technically what you're plugging into. Even though there was simplification, it's really this you're plugging into. And you can see right there, you're not allowed to make that denominator 0. X cannot be 0. Yeah, but it goes away. Yeah, but it goes away later. So initial plug-ins of 0 would be a problem. So x cannot be 0. So that's the main point I wanted to make there. When you answer domain questions for any combination of functions, added, subtracted, multiplied, divided, whatever, you got to answer the domain question before simplification. Before simplification. Make sense on that? All right, so I'm going to, and this is going to have to be it for our section. All right, 29. So this is super, super important, and I've got 2 minutes. Will be on exam number 1. Absolutely. Because it's the first thing you're going to do and when you begin calculus. Well, it's the second thing. Chapter 3, when you start calculus. It's the start of chapter 2, and then chapter 3 will have this right away. Super important. So let's take this function, f of x, which is x squared minus 4x plus 7. And they're asking me to find this right here, which is called the difference quotient. Difference quotient. And so let's do it. I'm going to do it piece by piece. So first off, what's f of x plus h minus f of x? Let me do it in colors to make it more clear here for you. Minus f of x all over h. So here we go. F of x plus h. That means take the function and plug in x plus h. And then minus all of f all over h. Yeah. Everybody see that? So in other words, this right here is f of x plus h, and this right here is f of x. Everybody good right there? F of x plus h minus f of x all over h. Again, this is called the difference quotient. It's because it's difference, it's a subtraction, and it's a fraction, which means a quotient, a dividing. So they're basically saying it's the subtraction fraction. It's the difference quotient. But it is the difference quotient. It's the one used in calculus. So anyway, you got to do all that algebra now. So I'm running out of time in a big way. Let me just do this real quick. You just got to FOIL this out. I'm going to skip all kinds of steps. You got to FOIL that out. You got to distribute that. You got to distribute this minus sign through all of that. And then you got to cancel stuff. X squared cancels. 7's cancel. 4x's cancel. You're left with just and then you just simplify it from there. So I'm out of time. So we got to be done with that. So we're done with that. 1.3 and 2.1 are due on Thursday at class time at 9 a.m. on Math Excel. Not 2.2, which was actually on our agenda. All right, guys, have a good day. Hang on if you got a calculator question or something like that. Anybody get the calendar? They're up here.